Hello, everyone.
Hello.
Does anyone have any questions before we get started? I think we're finally getting used to the 12:30 schedule. It looks like everybody's showing up at 12:30. That's good. It actually just barely gives me enough time to get finished with the last class and get my stuff put up and then start this one. So I'm thankful you guys allowed me to push it back to 12:30. So today we're basically going to jump into chapter 5. Remember, you have an actual test. I think it's due tonight. So no, it's due tomorrow night if I remember correctly. So make sure y'all get that done. Don't forget. We might send out an email to remind everybody of my 241 class. I know inevitably I'm going to give somebody a 0 because they didn't take their test. It's going to make me upset. So no questions on anything? No past homework questions or anything?
I had some homework questions, but I'm okay if you want to talk about those after class instead of right now.
That would work a little better for me if you don't mind. That'd be great.
Yeah.
Anybody that wants to stick around can stick around and see that then. So that's cool. All right, well, I guess we'll go ahead in. What I want to tell you about chapter 5 is chapter 5 is actually called, let me double check what the title is. But this is where you start to do stuff, is using Newton's laws, friction, circular motion, drag forces. So those are the big topics. It's all Newton's second law. I mean, or all of it's Newton's laws of motion, basically. So I want you to keep in mind, that's what we're doing, you know, once we got to chapter 3, or chapter 4, we were doing nothing but dynamics using Newton's laws. After this, we'll learn a way to do it with energy methods, which again allows us to do things without vectors, but with scalars. So that's kind of nice. And then we'll go on to relativity and some other things. We'll talk about circular motion and torque. But right now, we're going to start into using that normal force that I talked so much about, specifically for you guys to be prepared, because the normal force is actually proportional to the friction force. That's sort of the crux of why we needed to do it. Plus, you need to realize that it existed or the world doesn't make any sense. So we did that. Now we're going to actually apply it to cases of friction and stuff of that sort. So what I want to start off with is I'm going to try to convince you guys that there's two types of friction that we're going to deal with anyways. There's actually a rolling friction too. That's an entirely different scenario. But we have two types of friction we're going to deal with right now. And one's like a sliding friction, what we call kinetic friction. And then the other one's a static friction. And that's the thing that keeps something from moving relative to what it's touching. The kinetic friction, on the other hand, is the one that slows something down, even though it's sliding. So if you throw a 2x4, slide it along a parking lot, it'll slide for some minimal distance. But the fact that the 2x4 is moving relative to the parking lot tells you it is a kinetic friction. And I'm going to convince you guys that that kinetic friction is actually a lot weaker than the static friction. So what I want you to do is, hopefully you'll have either a heavy book with a desktop that you can slide it across, or perhaps a phone with some kind of more soft rubber around the edges. Like I got my OtterBox has this slightly outstuck portion that covers the screen, and I can lay it on the actual surface, and those edges of rubber make it grip a little bit better. Or if you have a calculator, maybe you have the one with the little rubber nipples on it, so they can actually stick again to the surface. What I want you to do is take whatever you're going to use to slide across that surface, and I would just want you to take your pinky, say, and give it just a slight push, not enough to make it move, but just a slight push, and then give it a slightly bigger push and a slightly bigger push, and keep on doing that until you finally get to a push that it actually moves. And that'll let you see that static friction, the friction of not moving, okay, that static friction supplies exactly as much force as necessary up to some limit. And I'm going to give you a graph of that in a second. And then once you finally get it moving, I want you to continue to push it a little bit and see how much easier or how much less forceful the friction force is once it starts moving, because once it starts moving, you're dealing with kinetic friction. And there's a lot of reasons to know this. One of the most convincing, I think, is the fact that your meteorologist tells you every winter, or just about every winter, when we actually get snow, which in this area is not that often, but when we get snow, they tell us, make sure you turn into the skid. And what that means is when the car is skidding around like this, say, then your tires should turn that way to try to recover the kinetic, or excuse me, the static friction instead of the kinetic friction. So I'm going to first convince you that the friction between your tire and the road is a static friction, which a lot of people seem to think is really odd, and I get it. It doesn't seem right, but it is. And then I'm going to give you a little bit of intro into that. So let's go ahead and begin. I'm going to start with using the idea of a car rolling down a road, and I'm going to use the addition or relative velocity formula to figure out that the velocity of the bottom of the tire with respect to the road or with respect to the earth is 0. Okay. So that's going to be kind of odd, but once we do that, then we've established that the bottom of the tire is in a static friction scenario, and that's the truth for all 4 of your tires, or 2 if you're riding a motorcycle, or 3 if you're riding a trike or whatever. Okay, so what I'm going to do is I'm going to draw a blurry picture. Okay, hopefully that looks better. All right, so you can imagine the tire of a car as this circle. Okay, so that's the back end of a car, say. And let's say the car is actually moving. This is the velocity of the car as seen by Earth is moving. And I'm going to call it a vector because we're dealing with one-dimensional motion, and just being positive is enough to give it a direction. So this is going to be moving at 60 miles per hour that way. Okay. That means also that the axle, though it may be spinning, the center of it is moving at a constant velocity of the center, E. Notice I use the exact same symbol because it doesn't really matter, is equal to 60 miles per hour. So that's the first part we got to see. And I think that all should be pretty obvious to people, right? You see that the center of the tire, since it's going along with the vehicle, the axle's not being left behind, then it must also be going at 60 miles per hour. Now what I want to do is imagine that same car sitting up on a lift. And of course, this is really dangerous. You don't want to crank up a car and run it up to 60 miles per hour while it's sitting on a lift in a garage. It's a potentially dangerous situation. But we're going to do that. We're going to, at least in our mind, do that. So what I want you to do now is think about the car sitting on this lift. So we got a big lift like this. That the car is sitting on. And I want to rev up the engine until the tires, until the speedometer says I'm going 60 miles per hour. I think what you will see then is that the velocity of the top of the tire with respect to the car is equal to positive 60 miles per hour again. And I bet you would say that the velocity of the bottom is going this way. What would y'all say that velocity is?
Negative 60.
Negative 60.
Exactly. Negative 60 mph. Okay. So that's what happens when it's on a lift. So really, to find out the velocity of the bottom of the tire with respect to the earth, then I can use my relative velocity formulas, which just says, long as this is the first subscript and this is the last subscript, and as long as the middle 2 subscripts match each other, then I get a valid formula. So I'm going to say velocity of the bottom, leave it blank, plus velocity, leave it blank, and then put earth for the last one. So you see the outer subscripts work. Now I just need something to put with this. Well, I look up here and I see that the velocity of the bottom with respect to C is a thing. And then I also see the velocity of C with respect to earth is the same thing. So I'll put the C here. Does everybody recognize as the proper formula for relative velocity?
Yep.
So now you can see that the velocity of the bottom with respect to Earth is negative 60 miles per hour plus 60 miles per hour, which equals 0. Okay, so yes, tire normally is in static friction. Okay, and there's actually a word, there's two names that I can think of immediately that are what you'd call the situation where the tire has a relative velocity that's not 0 relative to the ground. Both of those, the one word version starts with an S, and the first word of the second version starts with an S. Can anybody think of what that's called when the tire is not actually moving 0 with respect to the road?
Burnout.
Yeah, that's a B word, but yeah, but burnout, spin out, skid, that kind of thing. All those are different ones. So skidding, sliding, the spin outs, burnouts, all those things are things where static friction is not happening, and static friction is the one that is the most powerful. The other thing I want to show you, just for to make some sense of why you don't necessarily want your vehicle made like monster trucks. Like, I mean, it kind of looks cool in some way, especially if you're redneck like me. It looks kind of cool to have your tires like that, right? But if they're not inside a wheel well, watch what happens with the top of the velocity. So the velocity of the top of the tire with respect to Earth is equal to the velocity of the top with respect to the car plus the velocity of the car with respect to Earth. And you can see that's going to be 60 mph plus 60 mph equals 120 miles per hour. So if you're on the side of the road and this guy flies by you at 60 and has a rock embedded in the groove of his tire, if that rock were to sling loose, it's going to hit you at 120 miles per hour coming out in front of the car, right? Alternatively, if you're sitting inside and just got your little elbow hanging out the window, say like this, because, you know, that's what we do as rednecks, little steering wheel driving like that. Okay. If you're actually hanging out like that, now the rock moving relative to the car is just 60, but it's still going to hit you in the arm at 60 miles per hour, which I don't think is very pleasant either. So that's another scenario that we can discuss, that I thought we should discuss. Now, the reason that they tell you to turn into a skid, I'm going to use as a model, I'm going to use my calculator. So here's a car riding along. So we're looking at a car from above. Yeah, and he starts to go around a curve. Yeah, that's supposed to be normal, right? Well, when you skid, I'm going to let this this little red part represent the front left tire. So normally you're riding like this. If you need to take a turn, you turn your wheel a little bit, and then that turns the car like this. If you're coming around a curve, then what you're doing is your tire's a little bit that way, and you're slowly going around a curve. But as you start to spin out, what happens is this end goes around like this. And if you don't change your steering wheel, the wheel stays like that. But what the meteorologists tell you to do is to turn into the skid. So what they mean is when the back end comes this way, you should turn your handlebars. You should turn your steering wheel this way. And the reason why is if you haven't gone too far, then you can realign this tire with the direction of travel and reestablish static friction as opposed to kinetic friction. And that's why we say turn into a skid. So the rule is, remember, you start to slide this way, your back end's going to the left, so you better turn left. And you can see cars doing that all the time on dirt tracks and stuff like that. Or if you watch the movie Cars, you can get sort of the same lesson, only they don't give you the same reason. So they were actually pretty correct in that. If you want to go right, you got to turn left, right? That's the way they made it goofy. But in reality, that is the truth. When your tail end starts to pull out to the left, you want to turn your steering wheel to the left as well, in hopes that you haven't gone so far that it's too late. If it's too late, it's just too late, and maybe that's not going to help you at all, but maybe you can get enough friction where it'll slow down, and then as it slows down, the back end will slow down and the front end will grab again, and you'll be good to go. So with that in mind, let me give you a graph of the friction force. Remember, I used the script F for friction. So the friction force in newtons, I'm going to make a graph of that versus the applied force. And that means the force applied to the object we're talking about. So I'm just going to call that symbol F, and that's also going to be in newtons. And this is the force applied. Now, if you did the demonstration I asked you to do, then you know when the vehicle wasn't moving, or when the, whatever you use, the calculator, the phone, or book, or whatever, when it wasn't moving, the friction force just gave the exact same force as the force applied. So that's like the line y equals x. So it's a 45-degree angle like this. But then eventually you get to this one thing that I'll call F max. And once you get to there, all of a sudden the force will drop to some other quantity. And this quantity turns out to be F kinetic. And F kinetic is mu kinetic times the normal force. And F max is mu static times the normal force. Okay. So really the equations that we're working with is that F static, which I'm going to write as Fs from now on, is less than or equal to mu static times the normal force. And then kinetic friction is mu kinetic times the normal force. And mu s is always greater than mu k. So that's why we turn into a skid, is mu s is larger than mu k. So now let's use that to, yes.
Can you zoom in a bit?
Yes, I can. Evidently, I got all cocky with my skills and dropped 3 pins, and now I'm messing up the paper. Hold on. I just looked at what I wrote, how the page was moving. I'm sorry. That made me laugh a little bit. Sorry. Okay, is that enough? Did you see what you were going for?
Yes, sir.
Sorry about that. I literally dropped like 3 pins. I was trying to keep one from messing up my clothes, and then I almost fell out the seat. Oh, it was exciting on the side. All right, so let's solve a simple problem. This is a kindergarten level. Again, I do that just sort of let you guys know it's supposed to be easy. If I ask you a question about it, you should be able to answer it because it's supposed to be that simple, that sort of thing. I'm not meaning it as derogatory if you don't understand it. That's the key thing. So this is example 1, and I'm very impressed with my writing of the word example. I'm working on my cursive writing. I want to make sure it gets better. So example 1 is going to be a 100-kilogram crate. And I put that digit after the 0, not because I really want 4 sig figs, but because I want 3, and I didn't want to write the stupid 100 dot. Okay. And it's going to be on a friction full surface like this. And there's going to be a force applied to it that is not exactly horizontal. In fact, it's going to be up at an angle of 36.9 degrees. I don't know why I wrote the dot up there. I may be mentally handicapped. And the force is going to have a magnitude of 100.0 newtons, and it's 0.0 for the exact same reason that one was. Okay. Now, whenever you see 37 degrees or 36.9 degrees or 53 degrees or 53.1 degrees, you guys should immediately think of the 3, 4, 5 triangle. And that's what's happening here. The 3 is down here, the 4 is up here, and the 5 is over here. And this angle right here is opposite the small side. So that's the 36.9 degrees. And this one's the 53.1 degree angle. Now you can tell my magnitude's 100, so I have to multiply 5 by 20 to get 100. So that means really, if I'm thinking about this, I want to multiply each of these by 20, and then I'll know how to do the component stuff. It'll make life a lot easier. So that's my object, and I want to calculate, I want to determine, is there acceleration? And if so, what is A? Okay. So I'm going to start with a free body diagram because that's the way we use Newton's second law is with free body diagrams. So I'm going to put right here, I'm going to put a mass M, which equals 100.0 kilograms. And now I'm going to draw my coordinate system such that up is positive y and right is positive x. And I'm going to draw my forces on it as follows. Notice this one has not been along an axis, so it stays black for me. That angle, of course, is 36.9 degrees. Trying to write it big enough so you guys can see it. Now, the forces acting on it that I know, for instance, is the normal force, which is a vertical force upward. So I wrote that purple to represent positive. The x component of this force is, in fact, notice it's adjacent to the 36.9 degrees. So just like the 4 is adjacent to it, so 4 times 20 would be 80. So this is 80.00 newtons. And similarly, I normally would put this right here, the y component, but putting it right there is going to cause it to be written right on the 36.9. And then last time when I was doing this, by putting it over here, I missed it when I was doing my forces. So I'm also going to make sure I just put it over here instead. And that one's going to be 60.00 newtons. Okay, I know I wrote that small. That's 60.00 newtons also acting in the upward direction. And that's the component of the force I'm applying in the y direction. And the 80.00 newtons is the force I'm applying in the x direction. Okay. So I could also say this is the 60.00 newton force here. Just don't want to count it twice. That's the main thing. So I drew it over here just to make it a little more clear. Now, with that in mind, I also know there's a friction force that if I'm pulling the object this way, the friction force is going to try to oppose that motion. So it's going to act this way, but I can't do anything other than just call it F because I know it's going to be a friction, but I have no idea whether it's static or kinetic, that sort of thing. And then finally, I have one more force acting on it, and that's the weight of the object, which is M times G, which is 980.0 newtons, again, carrying one extra digit. Now you might think, well, horizontal motion, that's the only acceleration we care about. I don't even need to write an equation for the y direction, but that's what I've been teaching you the normal force stuff about, is so we can do that, and we have to do that here when we're dealing with friction. So what I'm going to do is calculate Newton's second law for y motion, and we're going to remember that the box is not going to be bouncing up and down or anything like that. So there's really going to be no acceleration in the y direction. So the summation of the forces in the y direction equals mass times acceleration in the y direction. Really says the summation of forces in the y direction should be 0. So that's what I'm saying. Now I can write all the positive ones, which I see is Fn plus the 60 newtons, either that one or that one, whichever one you want to do. And then the only other force in the y direction is a negative, and that's 980.0 newtons. And that's all equal to 0. So I immediately get that the normal force, notice when I move that number over there, it becomes positive, and this number becomes negative. So I get 920.0 underscore newtons is the normal force. So this is another instance where the normal force is not the weight. Remember, we've talked about inclined planes. The normal force is not the weight. In fact, it turns out to be mg cosine theta. And I've talked about normal force when a force is acting upward on it, then the normal force is decreased. If a force is acting downward on it, then the normal force is increased, all that sort of stuff. So here's another instance of that, where by lifting slightly upward, I'm decreasing the normal force, and therefore I'm actually decreasing the friction force too. So does everybody understand what we got so far?
Okay, so you're saying that you now that you've applied the force to the object, you're changing the new normal force due to that.
Right. Yep. Because this rope was pulling up on the crate upward a little bit, it's assisting the normal force. So we ended up getting, instead of 980, which would be the weight, we got 920. Now what I need to do is figure out what the summation of the forces in the x direction is. So I'll say summation forces in the x direction equals mass times acceleration. Now there's no other acceleration, so I'm just going to call that a instead of a sub x. And we don't know, is this 0 or what? Okay, that's what we don't know. So I'm going to put all the forces acting in the horizontal direction, and I'm going to see that's 80.00 newtons. And the only other one is minus the friction force. But what we can do now is, now that we know Fn, this implies that F max, sorry, I was supposed to write that as a script F. F max is equal to mu static, which for some reason I just chose not to tell you guys. It's equal to mu static times the normal force. Well, what I was choosing for mu static was 0.50, and what I'm choosing for kinetic is mu kinetic is equal to 0.20. So that was the part I should have gave you, and I didn't give it to you till now. But anyways, we now know it. Okay. So you can see that the max force that friction can put out would be 0.500. Actually, it's supposed to be 50, 2 sig figs, times 920.0 newtons. So that's going to be 460 newtons. So if we look back at our graph, we see this is 460 newtons for this particular problem. And the actual force that is applied is 80 newtons. So I know that's less than 460, so I'm just going to go here and back to here, and that's going to be 80.0 newtons, because that's what this graph tells us. So I can now write 80 newtons minus 80 newtons is equal to 0. So A is equal to 0, and no is the answer. Any questions on that?
What's the coefficient of static?
That's 0.50,
Okay.
and this one's 0.20.
What's U static?
0.50. Okay. So if this force had actually exceeded 460, then I would have said, okay, the force is going to be the static force, and I'd have to calculate 0.2 times 920. Okay. And then I'd put that there, and then I put MA over there. But since I got 80 minus 80, which is really what the physics tells you is going to do, then I knew the acceleration had to be 0. Does that make sense to everyone? Now, those of you considering a career in engineering that may have to take statics and dynamics, in those courses, they'll teach you an algorithmic way to deal with this, less than or equal to symbol. And they'll have very specific steps for you to follow. And it's just a simple little algorithm. It's really nice and makes the physics a lot easier. And I support that as someone to teach an engineer. That's a good thing to teach them. Because engineers, we want them to be creative, but we want them to also know somewhat what the limits are. And the limits are, never be so creative that you're predicting the well-being of a building or a person based on a hunch that you had, okay? Unless that hunch has been supported by experimental evidence, which you can get from your journals and stuff like that. So in physics, we don't give you a little algorithm like that, because we want you to be able to fly by the seat of your pants and be creative and figure out ways to solve it. This is the first time, this year is the first time, this semester is the first time I've ever done it this way, where I start off with this graph and just, go back and point to that. When I find out what the force is, I go back and jump here and see if it's less than 460. If it is, then I do that. That's a nice, neat, comprehensive way of doing it. First time I thought of it, and the first time I did it again is this semester. So I also think it's appropriate for us physics teachers to do it that way, which is different from the engineers. And then part of it is, when you get to the engineering fundamentals exam or for the licensure exam for engineering, you're allowed to take any number of books with you. So your books actually give you these nice algorithmic ways, so you can quickly flip through it and say, oh yeah, what was that algorithm when I have a static friction scenario? And you look that up and you solve the problem real quick, and then you get your license. Okay. So I think I support it both ways. I support the way the engineers are doing it, and I support the way us physicists are doing it. I think it's perfect for both of those groups to do it the way it's being done. So anyways, just know it's going to be a little easier when you get to the statics, dynamics, a little easier in the sense that you don't have to figure out a way every time, but a little harder in the fact that you're going to have to memorize an algorithm. So let's try example 2 now, but this one's almost the same thing. I'm just going to increase the force that I'm applying. So I'm still going to take the 100 kilogram crate. I'm still going to have a frictionful surface with 0.5 and 0.2 as my coefficients of friction. So I'll say mu static is equal to 0.50. Mu kinetic is equal to 0.20. And instead of using a force of 100 newtons this time, I'm going to use 1,000. Okay. So I'm going to say the force is 1,000.0 newtons, which is really only like 225, 230 pounds, something like that. So it's really not that big a deal. But still, I did make it extensively larger. Okay. So this is the original problem. I want to know the same answers. Will it accelerate? If so, what is A equal to? Okay, that's their problem. I draw a free body diagram again. Again, I'm thinking that 3, 4, 5 triangle. So in this case, now this time it's going to be 3 times 200, because 5 times 200 gives me 1,000. And this one will be 4 times 300, or excuse me, 200. And this is the 36.9 degrees. Okay. So my free body diagram is going to be this. My vertical up is the positive y. My to the right is the positive x. My positive forces acting are the normal force, F normal. I have this force at 36.9 degrees of 1,000.0 newtons. So that can be interpreted as 2 positive components. So I'll have this right here is, remember the one adjacent is the 4. So that's the 4 times 200 is 800 newtons. And really, I'm using 36.9, so that's only 3 sig figs. This one, on the other hand, is 600 newtons. Okay. Now, my negative forces are, again, we don't really know anything about the friction force, except that it's a friction force right now. So I'm just putting F. I mean, y'all can probably guess already what it is, but we're pretending like we don't know yet. And weight, which equals mg, is still going to be 980.0 newtons, carrying one extra digit. The summation of forces in the y direction equals mass times acceleration in the y direction. That again has the y acceleration equals 0. So I'm going to say Fn plus 600.0 newtons minus 980.0 newtons is equal to 0. That gives me the Fn is equal to 380.0 newtons. Which means F max is actually equal to 0.5 times that. So you can see F max is actually going to be 150 plus 40, it'd be 190 newtons. And really, that's an extra sig fig, by the way. So now that I know what F max is, I can make a guess at what the friction force is going to be. The F max is 190. My force that I'm pulling it to the right is greater than that. So we're on the part of the graph where I've exceeded the max force, which means kinetic friction will act. So F kinetic, since 800.0 newtons is greater than 190 newtons, F equals F static, which is 0.20 times 380 newtons. Remember, 2.2 is the same thing as 2 over 10. So if I move the decimal one place here, it'd be 38, and then I multiply that by 2, and that'd be 76. So it's equal to 76.0 newtons is the friction force. So now I can take the summation of the forces in the x direction equals mass times acceleration. Again, I'm not subscripting the x because that's the a with an x, because that's the only acceleration in existence now. So now all I have to do is put the forces on the left and the ma on the right and solve for a. The forces on the left are 800.0 newtons minus 76.0 underscore newtons. That's the only two horizontal forces acting. And that's got to be equal to 100.0 kilograms times A. So we can see that A, notice when I subtract 76, I'm going to get 724. And then I'm going to divide that by 100.0 kilograms to 3 sig figs. So I get 7.24 meters per second. Every second is the acceleration. And I could put a 0 after that as my extra digit if I wanted. It's not a significant digit, but you just know that doing the calculation, if you needed this number somewhere else, you just use 7.240. That's the whole reason I carry that extra digit. Any questions on that? Let me back it up so you can see the whole thing at once. That's pretty straightforward, right? It's not that difficult. So the next thing that we're going to do is I'm going to try to introduce this other big topic. So remember, the chapter's called Using Newton's Laws: Friction, which we've covered, circular motion, which I'm getting ready to cover, and drag forces I haven't covered yet. But I'm going to go ahead and introduce you to circular motion. And I do it a unique way that I've been doing it for a couple of years, and I find it kind of fun. And I think students get it to some extent, but it's also a chance for you to use your calculus. So that's why I like to do it. I think I can do it right here on this page. So I'm going to attempt to do that. What I want you to imagine is a XY coordinate system. like such. Okay. And now what I want to do is draw a really good circle. So I made sure I did not bring a compass. That would not be useful at all. I'm going to draw a really good circle. I'm going to make it about like this, which has already gone way off track. But anyways, there's a circle whose center is right here. That's ideally what that's supposed to be. It turned out to be an egg, or at least something with a bad head injury. Okay. So what I'm going to do is I'm going to introduce you to something neat. I'm going to introduce you to a position vector, which we've talked about before when we started doing projectile motion. I said we can use x of t, or normally r of t. I'm going to use r of t. And I'm going to give it to you, and then I'm going to allow you later to go ahead and plot for these various times what the x and y coordinates are. So r of t is going to give us an x component of a vector, which you can imagine right here as this guy. Okay. That r of t is going to have an x component, r sub x, is going to have a y component, r sub y, like that. And of course, if this is the angle theta, you can see it's r sub x is going to be r times cosine theta, and r sub y is going to be r times the sine of theta. Let me make that theta bigger. Okay. So to do this, I'm going to use something other than theta because I want to bring in the time variable. So r is going to be the radius of the circle. And then I'm going to write cosine, but instead of theta, I'm going to write 2 pi over capital T. Capital T is going to be, I've designed it so that capital T will be the time required for this to go all the way around one complete rotation. So T is equal to the period. Okay. And in fact, by doing it this way, I'm actually going to get a nice problem where an object is going in a circle at a constant velocity. And I'll even show that that's the case. So that's the x component. So I'll put an I hat next to it. The y component will be the same thing, but with a sign. So I'll write r sine 2 pi over t times t. And that is really the best way to look at it and use it, as long as you are as long as you're doing trying to fill out the coordinates as a position as a function of time. Now we can also define omega, which is called the angular speed. It's like measured in radians per second. We can say that's 2 pi over the period, because that means 2 pi radians, and the period is the time required to do it. So that'd literally be radians per second, right? So we can rewrite this as omega t, and that works really well when we're doing our derivatives. So I'll write r cosine omega t I hat plus r sine omega t j hat. That's our position vector. Okay. Now, what I want you to do on your own is I'm going to say x comma y. That's your data points. And the time t is going to be, let's say t over 8. Well, let's start off with 0. T over 8. T over 4, which is 2t over 8. 3t over 8. T over 2, which is 4t over 8. Dot, 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 all the way up to t. In other words, go by increments of t over 8 and fill in all these points. And I think it'll make sense to you. This one turns out to be 1, 0. This one turns out to be root 2 over 2r, root 2 over 2r, like that, for t over 8, and so on and so forth. But you basically get this spot, this spot, this spot, this spot, this spot, this spot, and this spot, and then back to that. So just keep doing all those, fill those out, and you'll convince yourself that it is in fact a circle and that the object is going this way around it. Okay. Now that we do that, I'm going to use something we know from kinematics, and that is V of t is equal to dr of t dt. So I want to compute that derivative. So can anybody tell me what the derivative of r cosine omega t is?
R sine of omega t times omega.
And the one thing you forgot was
It'd
the
be
negative.
negative
But yeah,
too.
absolutely right. So this will be negative r omega
Omega cosine.
cosine. Oh,
Omega
excuse me,
t.
sine. Sorry about that.
Sine. Omega t, yeah.
Yeah, exactly right. And you use the chain rule. And notice the advantage of using that omega. You don't have to write 2 pi over t and all that crap. But the big thing, what you're taking here is remember the I hats and J hats and K hats, they're really constant vectors. So unlike spherical coordinates and cylindrical coordinates and polar coordinates, those vectors depend on position, and position can depend on time. So you have to do a chain rule with those. But when you're using I hat, J hat, and K hat, they're just like a constant. So you don't even have to worry about the derivative of that. Now, what's the derivative of r sine theta, sine omega t?
R omega t cosine of omega t.
Yep. So r omega cosine omega t. Now, here's the neat thing. If I calculate the magnitude of v of t, I get just plain v of t. That's another way of writing it. Now, what I do is I take the square root of those things. So I write negative r omega sine omega t, square that, plus r omega cosine omega t, square that, and then take the square root of all that junk. Anybody want to take a guess what that turns out to be?
Probably going to use your identity of sine squared.
2
plus-
pi r over t.
Yeah, the sine squared plus cosine squared is going to be 1. And since you have a common factor of r squared omega squared, you can factor that out in front. And then it'd be r squared omega squared under the square root times parentheses sine squared plus cosine squared. And what is sine squared plus cosine squared?
1.
1. So you don't have to do anything with that, but now you have the square root of r squared omega squared. So you just get r omega. And r is a constant, omega is a constant. So you see the velocity is in fact a constant. And if you actually took the time to print it or to plot it out, you would see that the velocity is actually a vector that's tangent to the circle at each point. In other words, at this time, it's going to be there. At this time, it's going to be there. At this time, it's going to be straight down, so on and so forth. So that's something else you can see, which would be quite nice. So we see the velocity is a constant. And also we can see by remembering what omega is, it's equal to 2 pi over t is omega. Now I multiply that by r. What is 2 pi r with respect to that circle?
Oh, 2 pi r.
2 pi r is the what?
Circumference.
Circumference. So it makes perfect sense that the velocity is the distance traveled, 2 pi r divided by the time taken. So that's something that comes in handy as well. So now we've got the velocity. That's not really what I was going for, but it is the first step to getting what I was going for. What I'm going for is the acceleration, because it turns out in order for this thing to actually follow this motion, it has to accelerate inward. It has a centripetal, centripetal, notice I'm using a centripetal acceleration. So A of t is equal to dv of t over dt. So now I'm going to take the derivative of the velocity. Anybody give me the derivative of negative r omega sine omega t?
Negative r omega squared cosine omega t.
Exactly. And then remember the I hat's just a constant, so that comes out in front. And then what about the derivative of r omega cosine omega t?
Negative r omega sine omega t. I mean squared. Yeah, omega squared.
Yep.
Sine of omega t.
And again, the j hat is a constant vector. You might also notice this is kind of interesting, and it's helpful to realize this is literally just negative omega squared, and omega being, 2 pi over t, that's a physical quantity. And therefore, when you square it, it can't be negative. So I've got a negative number multiplied by what's left of this vector. Notice that's just r of t. You'll see if I factor out the negative omega squared, I just get r cosine omega t plus r sine omega t, which is the original r I had. So that tells you this vector is actually pointing the opposite direction. That's the a of t vector. And it's called the centripetal acceleration. And you can actually work out its magnitude. You can say, for instance, the magnitude of a of t. It might depend on t. You don't know, right? But it's just going to be a of t. And lo and behold, when you do that, you get the square root of r omega squared cosine, or excuse me, omega squared cosine. All that's going to be squared plus, and there's a negative in there as well, plus negative r omega squared sine, same junk inside, squared, square root of all that crap. And you can again see that when the negatives are going to disappear because you're squaring it, the sine squared and cosine squared is going to give you 1. So all I'm left with is r omega squared quantity squared under the square root. So ultimately, that's just r omega squared. So you can see the acceleration is a constant. And one way you can write it is a centripetal is equal to r omega squared. But, and that's a valid equation. If you know omega and r, you want to use that one. Okay, if you know the radians per second, that's what omega is. If you know degrees or revolutions per second, you need to convert it to radians per second and then use it. But something you can also do is you can take that r omega squared and multiply it by r over r. And then when you do that, you're going to get 2 pi over t squared times r squared over r, which I think you can see immediately becomes 2 pi r over t squared times 1 over r. And what's that quantity?
V.
Yep. So we get v squared over r, and that is the centripetal acceleration. So both that first expression and that last expression are extremely useful. And you can see that, in fact, this is part of the reason why it's so hard to go around a curve very fast, because if you go around it at 15 miles per hour, you can make it with no tires squealing or anything else. But if you come back at 30 miles per hour, then the centripetal acceleration, and therefore the centripetal force required, which is the friction that your tires are supplying, that has to now be 4 times as large because the velocity went up by a factor of 2. And v squared would go up by a factor of 4. So you have to have 4 times as much friction as when you take the same curve at 15 when you do it as 30. If you went as far as 60, then it'd be 16 times. So if you try to take the same curve that you took at 15, but this time you take it at 60, it's going to require 16 times as much force. Also, if you take it with too small a radius, you're doing the same thing. You're making the centripetal acceleration get really, really big. So if you just still go 15 miles per hour, but you make it a half the radius of the curve, then you're going to increase the acceleration by a factor of 2. If you cut it down to a fourth, you're going to increase the acceleration by a factor of 4. So that's sort of the physics of all this. And I want to express this to you regarding the importance of this, this particular equation. For instance, there was a news story in the late 80s, but maybe early to mid 90s. I can't really remember, but a person who, you know, was one of those adrenaline junkies that like to do fun things. And people do this all the time now too. They'll go out to like Arches National Park in Utah and jump on some kind of big arch and throw a rope on it or some kind of cable or tie it around it and then swing off of it. And that's fun. I get it. I get that. So it's illegal. You shouldn't be doing it because there's one, it's danger, and the public parks don't want you to be in danger or whatever. But his idea was he wanted to do this, and he'd been doing it at all these cool places in California. And he took his friends, like him and 4 or 5 others, and they were all going to swing off the Golden Gate Bridge in San Francisco. Well, you probably don't know this, but one of the things about the Golden Gate Bridge is that's often used by, you know, people with severe depression or whatever for committing suicide, because the bridge is literally so high that if you fall off of it or jump off of it, it has the ability to kill you. It doesn't always, but it does have the ability to kill you. So it's an extremely dangerous thing to jump off the Golden Gate Bridge. Now, what his plan was to take him and his friends and tie themselves together with climbing harnesses and attach themselves to a cable and swing off of it. So he had this brilliant plan. And this is the danger, for instance, of everything. When you don't know something about stuff, you feel like you know a lot. But when you know a lot about stuff, you feel like you know very little. And that's sort of what happened to this poor guy. He didn't necessarily understand physics. And it cost him, in fact, I think one person died. One person became a quadriplegic for life. He got put in jail or prison or something. But his idea was to take a cable and attach it to the Golden Gate Bridge and then swing. Right? And that would be fun. Yeah, woo, yeah. And again, I think the Golden Gate Bridge people have made that outlawed now, but and it probably always was. But either way, it was a very dangerous situation, because imagine this. He took the time to weigh everybody. And let's say he found out that the total weight was equal to, say, 2,000 pounds. Or let's say for ease, let's say that's about 1,000, or excuse me, 4,000 newtons. Okay, actually, yeah, 2,000 pounds. I should have said the other way. It should have been about 250 newtons. Right? It's, yeah, the pounds are like 4 times bigger than the newtons. So yeah, sorry about that. That should be. No, the newtons are smaller, duh. So yeah, that's supposed to be 4,000. I think I'll go with the 8,000 instead, because I'm a goober and I didn't take time to calculate or think about this. I just thought earlier, about 2 minutes ago, to have it in newtons as well. So let's say he weighed his group, and he found out they weighed 2,000 pounds or 800 newtons. And he went to the local hardware store and found a cable with a max strength of, let's say, 3,000 pounds, which of course would be on the order of 12,000 newtons. Okay. So he said, all right, that's great. I have a nice little safety factor. I can attach my friends to it. We're going to swing. And that's exactly what he did. And it seems that, according to eyewitnesses, they got to about maybe this angle, something a little less than 45 degrees, and the cable busted. And the people fell off. One person hit a boat, which, as if the water wasn't bad enough, the person hit a boat, and that person, I think, became a quadriplegic for life, and that basically had no use of their arms and legs. I think another person died, not necessarily right then, but within a few months thereafter. The person that actually set everything up had actually did go to or did get convicted, and I think he went to prison for a certain number of time. And it was really a sad scenario, because he certainly didn't mean any harm to anybody. He just didn't know what he didn't know. And that's the nature of ignorance, is you don't know what you don't know. So that's what happened with this. And let me show you why that happens, because it turns out when you hang an object from a cable and allow it to swing, it's basically a pendulum. The forces you have acting on it, of course, are the tension in the cable, T, pointing that way, because it has to act exactly along the cable. And then you have a weight, mg, pointing that way. Well, we're going to choose a coordinate system that has x this way and has y that way. That means I'm going to have to realize that this being theta makes this angle right here theta. So, or actually more specifically, makes this angle theta. Sorry about that. The reason why is, notice this angle from here to here is 90. So that's 90 minus theta. So if this was 60, that would be 30. And then of course, this is a right triangle. So this one's got to be the co-angle to that one. Since that's 30, this is going to be 60. So you get back to where you're starting from. So with that in mind, we can see that this component of the weight is mg cosine theta. And this component of the weight, which is actually a positive one, is the one that causes the acceleration, and that's mg sine theta. So the summation forces in the x direction equals mass times acceleration gives me that basically the only force is mg sine theta is equal to m times a. And this is the tangential acceleration. This is the acceleration along the circular path. So I'll put a T on it. Okay. We're not necessarily going to work that out. I mean, you can see that A is going to be equal to G sine theta, and that's fine. But then you notice as theta gets larger and larger, the A gets larger and larger. In fact, you see the A tangential is equal to G times the sine of theta, and theta is going to be a function of time. Okay. Now the summation of forces in the y direction, this is where the important part comes in. You see that the tension is a centripetal force. It's the force that's going to have to supply the acceleration inward that we just learned about, that has to be necessary for an object to go in a circle. But it's also going to fight the mg cosine theta. So we're going to say T minus mg cosine theta has got to equal the mass. And in order for it to not stretch the cable and not break the cable, that acceleration has to be equal to v squared over r, the radius, or actually over L is what I called it. So over L. So you can see that the tension in the cable is not going to have to deal with just mg. It's going to have to deal with mg cosine theta, which cosine theta does decrease it a little bit, plus mv squared over L. And this term, because the larger the cable is, the larger this velocity gets, in fact. So this term is really not taken into account at all by that calculation. It takes a little account because the cosine theta makes the mg small. Remember, cosine theta looks like this for the 90 degrees. So until you get very close to 90 degrees, or actually initially it's going to be very large because cosine theta, oh, that's right, we started up here as this is 0. So when this is 0, the force is going to be mg. And did I say that right? That's that angle. Oh, okay. No, I did notice my theta is wrong. This theta does not match that theta. Sorry about that, everybody. Look, this matched that theta. So no. And that's going to force everything. I thought it was weird because earlier I got cosine in sine. So this one's going to be, in fact, not cosine or not sine. It's going to be cosine. Sorry about that. And this one, because this thing, this angle became theta, that would be, this is 90 minus theta. So this one's going to become theta. So purple angles are correct. Red letters too are correct. So this is now going to become sine theta. So what we get is T is equal to mg sine theta. That makes a lot more sense. Plus mv squared over L. That's the big thing. Yes. Now sine theta goes like this. And that's what was throwing me, because I knew I couldn't get mg at the top, which is when the angle was 0. That's how I figured out my error. So for the first 90 degrees, it's going to be 0 initially. So you're just going to have mv squared over r when you first fall. But as you get closer and closer to 90 degrees, you get closer and closer to the full mg. By the time you get to the full mg, the velocity is actually at its maximum. Just like when you swing on a swing set, your velocity is at a maximum when you're straight down, right here. So at that 90-degree mark, where the angle between horizontal and the rope or cable is 90 degrees, at that point, this mv squared over L is as big as it possibly can, and the mg is as big as it possibly can. So you get way more than just mg. That's why even if he gave it 1,000 pounds buffer, it wasn't enough. And like I said, the cable broke. Okay, we'll solve more problems like this, but I just wanted to give you an idea of how that works and how that comes into play when you're dealing with circular motion. Because in order for something to travel in a circle, it must in fact have a centripetal acceleration, and you don't get accelerations for nothing. They require forces. That's what Newton's second law says. The total force is equal to mass times acceleration. Any questions on that?
Can you go back to the equations, please? That was cool though, but can I see the equations?
Okay. So notice what I did was I drew a free body diagram for the mass. The forces acting on it were the tension that was acting along my positive y direction, which is a radial direction. And this is actually an accelerating reference frame, as you might imagine. And I made my x in the tangential direction, pointing downward, so the way it's actually speeding up. I measured my angle theta from horizontal down to the cable, but then I made this mistake right here, and that made all those red thetas, which are completely wrong. Once I corrected it, we saw that this component of weight was mg cosine theta, and this component of weight was mg sine theta. Then I took the summation of forces in the y direction and the summation of forces in the x direction. The summation of forces in the x direction gave me mg cosine theta, because that's the one pointing tangentially downward, is equal to m times a tangential. So if you're actually like had a speedometer, it would show your speed increasing as the angle theta increased. So that's where I get g cosine theta is the acceleration. And then if I wanted to actually calculate the summation of force in the y direction, I did. So I did t minus mg sine theta is the correct one. As I said, the red letters are right. The purple angles are also right. So I ended up getting t minus mg sine theta equals mv squared over L, because that's the acceleration it has to have to go in a circle. So ultimately, I found that the tension in the cable had to be equal to mg sine theta plus mv squared over L. And I argued that as v went up and up and up, as theta increased, in other words, v would go up and mg sine theta would go up. And of course, that force would be quite a bit larger ultimately. Right now, you could realize what V would be. For instance, if you wanted to know V, you could imagine V should probably be about the same as if you fell from a height L. So we can say 1/2 mv squared. No, we didn't do it that way. I was going to do it with kinematics, and I started doing it with kinetic energy. What I know is that V is equal to V0 plus AT, but that requires time. I don't have that. I do know that V squared is equal to V0 squared plus 2A x minus x0. That works as well. So, and this one has what I want. We started at 0 velocity, so the final velocity should be equal to the square root of 0 squared plus 2 times g times L. So V should actually equal to the square root of 2GL. I can plug that in and see that T max is going to be mg plus, when I square that, that becomes 2 mgl, because squaring that just becomes 2gl over L. So I can see that, in fact, it's going to be mg plus 2mg, or 3 times the weight of the group. So in reality, he didn't need to cover their weight. He needed to cover their weight times 3. And that did not work. So, all right, we're done for the day. You guys can split, or you can stick around. I know a student has a homework question, so I'm here to answer that, and I'll be here to answer any other questions.
Can you go to the
Thank you, Professor.
to the circular motion equations also, please?
Thank you. Yes. What were you saying about those motions?
Can you go to the equations? I forgot what the first one was. Is it position or is it speed?
Oh, there was this one was position of lot. Oh, you mean the R equals R of T thing?
I'm talking about the R times cosine 2 pi over frequency 1 divided by frequency times time I plus R times sine 2 pi divided by T times
gotcha.
T divided by.
So that was the circular stuff we did.
Yeah, circular motion.
Yeah.
So is
So
that
R
first equation? Is
R
that
of
first
T.
equation?
Uh-huh.
Is that position or is that what?
Yeah, this is position. It's position, which we often use the letter R for as well. In this case, it would really fit to be R because it turned out to be a radial vector for the position. So, but we often use R for position vector.
Okay.
Does that
So
make
this
sense?
Yes, it starts as position and it becomes speed and then it goes to acceleration.
Yeah, it actually became velocity. Then we calculated the magnitude, which a lot of people call speed. And then we calculated the acceleration and calculated its magnitude. So, you need to see more of that?
No, I just wanted to make sure I'm writing it all down. Thank you, sir.
No problem. All right, I've got it set up. Let me make sure I did it again. I've set it up now where multiple people can share the screen. So if you have a homework question, feel free to share the screen.
Okay.
You too.
Can you see my screen?
I can.
Cool. So my questions were with mainly with this one problem here, part A and part B.
Mm-hmm.
So you have the elevator with mass, and its maximum acceleration is like 0.061
Right.
g. So with this, do you want me to explain like what my thought process was, or
Yes, if you want to, or I can explain it to you, whichever one you want to do.
I'll just let you explain it to me because I already know what my thought process is. And
Okay. So what we have here is a problem of Newton's second law. We have an elevator that's actually going to be going up. I need the data. It says the mass of the elevator, M, is 4550.
yes, sir.
And it says the acceleration is 6.10 times 10 to the negative 2 g. And I want to make sure you understand that that g means 9.8 meters per second. So you got to multiply that 6.1 times 10 to the negative 2 times 9.8.
Yes, sir.
Okay. And they want to know, what is the max force? And then the second part,
Go ahead.
minimum. Gotcha. Okay, so I've got everything written down now. Can I steal the screen back and I'll show you what I do?
Go for it.
Okay, so what we have here is an elevator. And we have acting on it a tension T. And what we're going to do is we draw a free body diagram and realize that the tension T is in the positive direction. And the weight, mg, is in the negative direction. So the summation of forces in the y direction, which is the only direction, so I'll just write summation of forces equals mass times acceleration. That's going to give me T minus mg is equal to ma. Okay. So when a is a positive, you can see that T is equal to m times g plus a. That's the max case. But when it's accelerating downward, then T min would equal m times g minus a.
Oh, okay. Yeah.
Does that make sense?
Yeah, I think what the, because at first, my first couple attempts on that question, I didn't understand really what it was asking for. And then when I finally figured it out, I didn't multiply the acceleration by g.
Right.
So
Yeah. So that's all you have to do. If you just and I even factored out a g here. I do 4550 times 9.8, and then I'd multiply it by 1.061, and that'll give me my max. And when I do 1 minus 0.061, that'll give me my min.
yeah. Okay. So yeah, that makes sense. So I had one other question on another question we might have asked that.
Mm-hmm. I'm just going to calculate these right quick, just so we're on the same page. I got T max was equal to 47.3 times 30. I might as well let's say 310 newtons, and min I got 4550 times 9.8 times parentheses 1 minus 0.061, and I got 41.870 newtons for the min. So I don't know if that's what the answer they have is, but that's what it should be. And I suspect they're treating that as 3 sig or 4 sig figs, but this 3 sig fig should dictate it that it should be rounded to 1 decimal place, 47.3 and 41.9, say. Okay.
Yeah.
All right. So yeah, go ahead and give me the other question if you'd like.
Thank you. Let's see here. So on this one, part B, so we have a wedge with a mass m, and it's sliding down the wedge. And there's no friction involved. So it's saying find the magnitude FW of the force that the wall exerts on the wedge. So I'm assuming it means the wall here and not including the floor.
Right.
So that force is going to be equal and opposite to the force of the wedge on the wall, which is going to be a result of mass m. So that would be like if you construct a triangle, and you have angle theta in the bottom right, and you have your on the y-axis, you'd have your theta or sine theta m g in order to get your, and then in the x-axis would be sine theta, or not sine, cosine theta mg.
Yeah.
Yeah.
So what's going on here is you have a weight acting on the force of gravity acting on the mass m. and then the wedge has to support that. So the wedge is actually applying an opposite force straight up, mg, but that can be broken up into basically a normal force, which
Mhm.
is what the thing's applying perpendicular to itself. And then that normal force can be broken up into a vertical component, which is the force it's putting on the floor, or a horizontal component, which is a force that it's putting on the wall. So that's really what you're supposed to be recognizing. So it does turn out
Okay.
to be, you see, that's where the sine theta came in. You just got to remember which forces are what. The block is the wedge, since there's no friction, is only applying a force perpendicular to itself.
Okay, so the like for instance, so you have mg on the mass going straight down. That's going
Right.
to be the hypotenuse of the triangle versus one of the sides of the triangle.
Right. So let
Okay,
me draw
yeah,
in
that's
the
probably-
diagram.
Yeah.
I put the axis like this. This is the wedge. And let's say the
Mhm.
wedge has an angle theta. Okay. It's got a mass M on it. We know what's going on. There's a weight mg applied to the mass, but all the wedge knows is that, hey, I have to supply force to hold that mass up, and that force is going to be a normal force.
Yeah.
So the forces acting on the mass are the weight and F normal.
Yeah.
And that's it. So the normal force is really what the block has to do. So then you say, okay, well, the normal force has to have a component this way that the wall will supply, and a component this way that the floor will supply. So now all you have to do is figure out how this angle theta appears in that triangle. So if you follow this straight back, that's supposed to be like that. This should be the angle theta. That means this should be 90 minus theta. So this angle should be theta. So we should have the force on the wall should be Fn times sine theta.
Yeah, sine theta.
And then the force on the floor would be Fn cosine theta. That makes sense?
Yes, sir.
And then did it have it in terms of the mass of the block, or did it have it in terms of the normal force?
It has it in terms of the mass of the block and gravity.
Gotcha. So then you have to determine what the normal force is. And from the F equals ma, you can see that basically when we switch to this coordinate system, this is the angle theta, this is the weight mg, then that has a component this way, which is mg cosine theta, excuse me, mg sine theta. And then this way, which is m, because this is theta right here, that means this is theta right here. So yeah, this would be mg sine theta, and this would be mg cosine theta. So I'm getting like a cosine theta squared.
They're getting cosine theta times mg sine theta.
Yeah, cosine theta times mg cosine theta. Yeah, is that what they had as the right answer?
Oh, they had cosine theta and sine theta instead of cosine squared.
Okay, so let me check. Oh yeah, that's right. Because I got Fn, this is the wall force.
Yeah.
So now I know the normal force Fn from the summation of forces in the new y prime direction equals mass and acceleration in the y prime direction, which is that one, right? We see that the mg cosine theta comes in there. So the normal force Fn is equal to mg cosine theta. So the wall force should be Fn sine theta. And that's, of course, mg cosine theta times sine theta.
Okay.
Does that make sense?
Yeah, that makes sense.
Yeah, I think that's a good problem. I like it. It's sort of like that one I hinted to you guys about. If you do the inclined plane of angle theta, and then you put a little roller skate with an inclined plane of angle theta and put a scale on it,
Mhm.
And you have a person of mass M. Find out their apparent weight.
Like as they're rolling down the hill.
Yeah. And that's going to be like this in that you're going to get something more complex. You're going to have more than one trig function acting.
Yeah. Okay.
But both of
Makes
those are really
sense.
good problems.
Yeah, because so first you got to find the normal force and what component of the normal force is in the x direction, and then you
Right.
figure out what the normal force is.
Yep.
You plug that in. Okay, that makes sense.
All right.
So,
You got another question?
I had one more written down. I don't know if it's a question anymore. Let's see here. Where's my piece of paper? Here's my piece of paper. Let's see here. It was 2C. Let me pull that up. Okay. Let me share my screen real quick. So this one, you have a rope and there's this force and this force pulling on either side of the rope.
Right.
And it's asking what's the upward force, or find the magnitude of the upward force C, CU. So going that way, and the downward force on B, then you have BD. Why are these equal? Which of the Newton's laws say that? And so at first I had looking at Newton's laws, I would say Newton's first law, because if the sum of the forces equals 0, it's not going to move.
Mm-hmm.
But they're saying the third law, which is every action has an equal and opposite reaction.
Right. So the first law is what tells you there has to be a force. So you're right in that sense, but they're saying that they're equal comes from the fact that that force has to be equal but opposite to the force that you know. So that's why they're saying the third law is the right answer. Like I said, you could argue about it. It's all about the wording, but really you're right in saying that the force on the magnitude upward force C on C due to U, that has to be pulling upward on C, right?
Mm-hmm.
And then the downward force of FB on D, BD, where's D? Oh, down, gotcha. Yeah, that, okay, now I see, yeah. The downward force on B, gotcha, are equal. So the Newton's first law, you're right, is tells you that the total force must be 0, but it doesn't tell you necessarily what the forces adding on it are. So then when you look at the force FCU, that's supplied by the force on part C coming from basically 0.2 on the graph. I mean, on the figure, that's a force upward. And to show that that's the same as the force downward, you then had to realize, well, whatever force B applies to C, C must apply to D. That's Newton's third law.
Okay.
It's just opposite in direction, right? So yeah, that's why the magnitudes are equivalent. You just didn't know what those forces were with Newton's first law. It just told you the net force had to be 0, but it didn't identify any of the forces.
Okay, so for this one, you're saying, like, if you have this rope here and you have a person at one end pulling it and a person at the other end pulling it, FU is one guy and FD is another guy pulling it on either side.
Right.
The magnitude of CU, so some point on the rope towards the guy pulling at D, is equal to the magnitude of B towards the other guy.
Right. So Newton's first law, if you look at it and see that that the rope's not moving, Newton's first law tells you the total force must be 0. But it doesn't tell you what the forces are. Then you realize, wait a second, I know that the force by one guy is acting one way and the force by the other guy is acting the other way. and in fact, one of them's acting on the rope and the other one, the rope is acting on them, Newton's third law says that those two are equal but opposite. That's how you identify them.
Okay, so like if you had one end of the rope tied to a pole and the other end, the guy's pulling with 50 newtons, then that means the rope is pulling on the guy with 50 newtons as well.
Exactly.
Okay.
Remember that Newton's third law has to apply to different bodies. A Newton's third law couple, the two forces in a Newton's third law, they have to apply to different things.
Okay.
And the fact that one was applied to C and the other one was applied to D means that, or excuse me, one was applied to C and the other one was applied to the other part of the rope. They're different objects, so that's why Newton's third law applies to them.
Oh, and so Newton's first law doesn't apply because it would have to be the same object.
You're right. You're dealing with one object and all the forces acting on it.
Okay, so that's what because I was thinking of the rope as a whole versus like components of the rope.
Right, and that was kind of confusing because they did use C, but they didn't do B. Well, they did do B. Yeah, actually, they did do part B. So yeah, that's good because they're talking about part C of the rope versus part B of the rope. So yeah, that's why they labeled it that way. Some of the questions they ask you often to make sure you understand Newton's third law is when you step off a curb, you feel a force mg pulling you downward.
Yeah.
What is Newton's third law acting on? Because you're saying your force is downward. What are you pulling upward on?
The earth is moving upward.
Right. So that's the weird thing. So yeah, if you're talking about force C, the force on C, it's applying to B. Well, the B is applying a force on C as well. And the fact that you exchanged those meant that it was a third law set of forces.
Yeah. Okay, that makes sense.
Explains it. Anything else?
I think that's it. So
Right.
Thank you.
No problem. Have a good one.
You too.
Bye-bye.